Okay, so yes, we started talking about limits for that you did in Calc 1, and we saw that when you had a limit, it happened when if your input value was approaching the limit point from two directions, if the y values also reached the point L from both directions, then we had a limit. But we saw that when we were defining it for a function of two variables, now you have input variables that are points, two-dimensional points. And so we were saying that an arbitrary point, let me see if I can find my laser pointer here. An arbitrary point needs to approach your limit point, AB, but because now we're in two dimensions, there's not just two sides, there's infinite number of paths where you need to approach your point. And as you approach that point, AB, you want to see if your z values are going to approach a number L. And that's if that happens, then we say that the function has a limit as xy approaches AB to the value of L. Okay, but what made this really hard was that you had an infinite number of paths. So then we said, let's start with the easier question, which is when does a limit not exist? And so it will not exist when there are at least two paths towards AB that produce completely different z values. Okay? We did two approaches to that. There's two methods that I showed you guys. One is like literally creating a path. So we said, okay, for this limit, I want to approach the origin 0, 0. And we're going to approach the origin 0, 0 while we only use the x-axis as our path. So as points approach 0, 0 on the x-axis, and then when points approach 0, 0 on the y-axis. Okay, that's when we're using paths to figure that out. Online on Canvas, last week, let me go to last week, I then posted a video. I also put it in the announcements. But last week I posted another video of a different example approaching a limit point. I'm not going to show the whole video. It's probably going to show me ads.
This is Dave.
Anyway.
Head of marketing.
Yeah, whatever. You're approaching a point from a linear line with a particular slope or a parabolic path. So if you didn't look at that video, take a look at it. It shows you different ways of doing a problem like the one we did here, but instead you're using a parabolic path or a line. Okay. The other method that we learned was, well, let me consider x and y in polar coordinates, and notice that if the radius r is approaching 0, that's going to force x and y to both approach 0. And so this limit, which is in rectangular coordinates xy, will be equal to this limit, which is in polar coordinates as r goes to 0, because that's going to force this input value and this input value to go to 0. And so this other method, you don't have to find different paths. You just use this polar path and substitute everything in polar coordinates. And then we solved through a little bit of algebra. We run out of time, so let me kind of show you a picture here. So we're trying to approach the origin right here, right? And so because we're using x and y in polar coordinates, imagine there's a circle of radius r, okay? A radius r right here. And we do all our algebra. The r's ended up canceling, and we ended up with cosine of 2 theta. And then we wrote that this tells us the limit does not exist because we have totally different limits for different values of theta. Then we run out of time. Okay? So let me explain exactly what that means. Remember that you're still approaching the origin. Okay? If I pick a particular theta, for example, if I pick theta to be pi over 4, now this point that was here, xy, is going to approach the origin through this direction of theta. versus its theta is pi, let's say it's pi, theta here is pi. Now the point is still approaching the origin, but through this path here, through theta. So there's all these different theta paths that it could take. But what this is saying is that depending on the theta, for example, if I plug in pi over 4, what's cosine of 2 times pi over 4? It will turn into cosine of pi over 2, which is 0. But if I use this path where theta equals pi, what's cosine of 2 pi? 1. And those limits don't agree. That means that through this path, z is going to approach 1, but through this path, z is going to approach 0. So they again disagree. Do you guys see how if theta equals pi, you're on the x-axis, right? And what did we say is the limit when you're on the x-axis? What does the limit approach? Positive 1, which is the same, telling us the same story here. Okay, so that's what we're calling the polar coordinate method. Okay, it made it a little bit easier in terms of the algebra. You don't have to consider different paths. You just want to see if you end up with an actual number, or if you end up with a function of theta, then the limit will not exist, because depending on the theta, you'll get different limits. Okay, that's where we left off. And that's to show a limit does not exist. So, no warm-up today, since we got to continue where we left off. So let's see. All right, so let's keep going. So we're still in section 14.2. We're going to do limits, and then in a little bit we'll do continuity. All right, so in our last class, we showed how a limit does not exist. So the question is, how can we show a limit does exist? How can we show that? We're going to consider the extreme case where you're approaching the origin. And we'll start with that, okay? So in the case where you have points approaching the origin, we can use polar coordinates as we did earlier. This only works when you're approaching the origin, okay? Let's take a look. So this will look like a homework problem. It'll say find the limit, where we're going to do the limit as xy approaches 0, 0 of 3x squared y over x squared plus y squared. Notice we can't just plug in 0, 0, because then we get 0 on the bottom. So let's try using polar coordinates. So let's let x equal r cosine theta and y equals r sine theta. And do like what we did last example in the last class. And this limit will be the same limit as r going to 0, but now instead of x and y, we're going to rewrite everything in terms of polar. Our x is r cosine theta, we're squaring that. Y is r sine theta, and then we got r cosine theta squared plus r sine theta squared. And so then let's see where that takes us. Help me out here, make sure I do the algebra here. Is this 3r cubed? 3r cubed and just sine cosine, right?
Cosine squared.
Cosine squared, thank you. Cosine squared. Cosine squared, oh, that's right. And the bottom is r squared cosine squared plus r squared sine squared. What happens to the bottom?
That's all to the 1.
You factor out the r squared, and then you end up with cosine squared plus sine squared, which is 1. So then what can we do here? Any idea?
So you just factor, just cancel r squared up and bottom.
Yeah, let's cancel this one, and then we'll cancel 2 of those here. So then we end up with the limit as r goes to 0 of 3r sine theta cosine squared theta over 1. Nothing else cancels. So what's this limit? Oh, the only thing it's affecting is which variable? R. And it's okay to plug it in, right? So what does the whole thing become?
0.
In this case, everything will just cancel out to 0. So you end up with a limit of 0. So it doesn't matter which direction you're coming towards the origin, they all are going to have z approach 0. Okay, versus the other example we saw where if this r did not, if both r's would have canceled, then the answer would have been 3 sine theta cosine squared theta. And then that's when you get the limit does not exist, because depending on the theta, you get a different number. But the fact that this r stays here tells us that all the z values always are going to just get canceled off and go to 0. Okay? No matter which path you take, it'll take you to 0. This is only in the case, though, where you're going towards the origin. Then you can use this polar. And if the algebra is nice. Let me add that too, because if this was like log of x squared or something, like, and you got like trig and side logs and stuff, it might be a little bit of, it might be more challenging because the r's might not cancel off nicely. Okay, that's where it gets kind of nasty. Questions on that, this part? You guys see the difference between this one and the one from last week? One from last week did not cancel to just a number. Okay. Okay. So now the big question is, what do I do if I can't use polar coordinates and if we're not even approaching the origin, just in general, some point in general? Stop closing one. So
So you put I x equals 0.
say it again.
So you just put xy become x0 or 0,1.
For this problem, or for where we're gonna?
In general.
So in general, what about in general, if you have your point approaching just any arbitrary point AB? Doesn't necessarily have to be 0, either of those. So, let me show you a little picture of what that looked like. Got your point AB here, and then you're just trying to approach it from all kinds of different paths, whatever they end up looking like. Okay? And we won't be able to use polar coordinates the way we did here. So, what's going to happen? For some of these examples, you can. It's like really case by case. Like you can just sometimes you can do some algebra. Remember in Calc 1, you guys sometimes multiplied by the conjugates, you factored, and then like you were able to plug points in. You could try doing that, okay? but that's a very special case. So in general, what ends up happening is you have to prove the limit exists versus showing the limit exists. Here we showed the limit exists, which I guess it is like a proof, but we just directly showed it has to be 0. There's an actual formal definition of a limit that you may or may not were presented in a calculus class, okay? And so there's an actual formal definition of what a limit really means. And so that's what that's what happens with this case, is that it's not, we have to actually, you can't show it through some algebra, you're actually gonna have to prove that the limit will exist using what's called the formal definition of a limit, okay? I'm gonna show you the formal definition. I'm gonna explain what the hell it's trying to say. I will not have you guys do that though. I'm not gonna have you prove a limit exists. There's a video that I did post on Canvas of me showing an example of how I prove it, if you're curious how that works. Okay? Yes?
Will future classes need us to?
No. Unless you get to real analysis, which is a class you take once you transfer, where you then have proof as part of the homework. So then at that point, yes, you do have to prove it. Yeah. That's why I wanted to just kind of show you and expose you to it. And then if you take my class next semester, the transition to upper division math, we prove it in that class. Yeah. So first, let me go off of the definition, okay? So this is called the epsilon delta definition of a limit. It's a mouthful, so let me write it down and then I'll kind of try to explain what it's saying in English. So it says, let f be a function of two variables whose domain D includes points close to the point AB. So notice it doesn't necessarily say that AB has to be in the domain. It just says that there's points, it contains points very close to this point here. Those points around it are in the domain. Okay? Then, it's not then. The limit as xy approaches AB of f of xy is equal to L and let me stop for a little bit. Let me show you first what I'm going to write so it doesn't look too weird. And then we'll write it. So let me see if I can actually move this like that. There we go. Okay. Let me open this up. Oop. Okay, so this is what we're going to write. Okay. So as you're approaching the point AB, okay, and once you get really close to that point, then when that point is very close to the point AB, then the output values, the z values, should be z values that are very close to L. Is that cool? Right? If I'm a point, let's say Young Yang is the point AB, and I'm walking towards him, okay, and I get inputted into the function, then my z value, if the limit exists, then my z value needs to be close to the number L. And the closer I get to him, the closer my z value gets to the value of L. You guys kind of see that? Okay. How the hell do I say, in math, how do you say you get closer to the point? Say it again? Approaches. How would I mathematically write that way. What does it mean for me a point to be close to him? The distance between us gets smaller. Yes, David. Well, that's what we're going to define. That's what we're trying to define, the limit. So the closer I get to him, the distance between us starts to get closer and closer and closer, right? So what is closer and closer? This symbol is the delta symbol. And in math, it's going to represent a very small positive number. Okay? So when the distance between us is you say, within a delta distance away from each other, meaning very small positive distance from one another, then my z value and the limit value are close together through another very small positive number called epsilon. Okay? So I'm going to say that again. The closer I get to the limit point, which means that we're within a small positive delta distance, my z value and L are also within a small epsilon positive number distance, a small positive number. And so what's going to happen is, if it's true that the limit exists, then the distance between me and L through epsilon, if I pick a random little epsilon and I say I want my z value to be within epsilon distance away from L, then it has to be true, if the limit exists, that this point and the limit point are within a delta distance away from each other. And that will always be true if the limit exists. Okay? So let me leave that picture there. And let me write out the definition. So it says the limit blah 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 will equal L. Where's my other blue marker? If for every epsilon greater than 0, that's this bad boy, there exists a corresponding small delta greater than 0. In English, for every epsilon distance that z is within L, then there has to be a corresponding delta, so that me and the distance between the limit point are within delta units away from each other, where it's smaller, very small, okay? And then there's more. Such that if x, the point xy is in my domain, remember that's how you say is inside of D, is in my domain, and remember you guys said that me being close to the limit point means the distance between us? And the distance between the point x, y, and AB. So to do that, I have to do the distance formula. So the square root of x minus a squared plus y minus b squared has to be greater than 0, because it's a distance, but it has to be less than delta, because I'm within the delta units away from my limit. Okay? Then, how do you say the distance between z and L in math when it's not a point, it's just a number?
The difference.
The difference, but you want the absolute value of the difference. Okay? Then z minus L is less than epsilon, which means they're within epsilon units away from each other. It's a mouthful, like I promised. But I'm trying to translate it for you guys, okay? So if my z value if it's within an epsilon distance away from, if there exists an epsilon so that the z values are within that many units from L, then there has to exist an epsilon number so that my point x, y, and AB have a distance smaller than epsilon. But like I said, you have to prove all this stuff, which I'm not going to have you do because you don't know, you weren't formally trained on proving. And so that's kind of like a picture here. I have a little video here I wanted to show you guys. Where to go? Okay. Let me share this video here. See if I can make it bigger. Okay, let me play it. Let me see if it plays it. Uh-oh. Let me do it again. Bro. Okay, never mind. I can't show you the video. I'll post it though. I'm sorry. But it's basically what it's trying to show you. What it's trying to show you is, which I can't do, and I tried to see if I could do it on GeoGebra, but it was too time consuming. The smaller I make this epsilon, then this delta will change according to it. They're kind of like, they correspond to one another. The closer z gets to L, then my point needs to get closer to the limit point. That's only true if the limit exists. Okay, only true if the limit exists. Okay, and so I'm not going to expect you to prove this stuff. I will show a video of me doing one, but when you guys take higher level math, a homework problem or things like that, like prove these limits exist. Okay. So this is the formal definition of a limit. And it requires two proof techniques. One called an existence proof. You have to prove existence, and a direct proof where you have to prove an if-then statement. So it's like loaded with proof stuff. Okay. Anyway, I'll post a video of me doing an example proving a limit like the ones from the homework, something like this. But I just wanted to kind of show you guys and inform you that when you have to show a limit exists in general, it's a little bit more advanced. Okay? You're almost there though. You're like one class. Next class we could do it if you take it with me in the spring. Okay. So in terms of limits, I'm basically the homework. I'm gonna have you guys either show a limit exists this way in this manner, okay, or just show a limit does not exist in those cases. For something more extreme, I'm not gonna have you guys. I'm not gonna expect you guys to do it because it's a little bit gnarly. But what I do want to go continue with is continuity, to remind you again what that looked like using limits, and especially now that we have surfaces, what does that look like with surfaces? So here's the definition of continuity. We're going to say a function of two variables is called continuous at some point, AB, if we take the limit as xy approaches AB will there be a hole at AB? Just to remind you guys of limits. When you guys were doing limits, is the thing you're approaching in the domain or not in the domain? Could it not be? Look when you guys did this in Calc 1, right? If I took the limit as x approaches a of f of x, and I look at the graph, did we need a to be in the domain for it to be continuous? Let's say it was not in the domain. So you might have something like that. Would that be a continuous, would it be continuous there? No, right? There's a hole there. What if I defined it like this? Now A is in the domain. Is it continuous? No. Now what needs to happen? What do you think?
Like the limit should be exists at A.
That point needs to be where? Needs to be on the line, right? So the way you write that is you say, okay, A is part of my domain. It has to be defined at that value. But I need it to be defined exactly at the limit. So then it has to equal f of x. That's how you force the dot to be on the graph. So if we copy the same definition that you did in Calc 1 with Calc 2, what will we need this to equal? F of AB. So that the surface doesn't have a hole at AB, it literally has the point including it on that surface. So there's no hole or anything fancy there. Period. And then we say a function is continuous on a region D if it's continuous at all points A, B that are within that region. And so in this class, a lot of the functions you're going to deal with are going to be continuous within a region. And so the following functions are all continuous on their domain regions. So polynomials, rational functions, root functions, and then we got exponential functions, log functions, and then we got our beautiful trig functions. Okay, so for example, this rational function here is continuous on its domain, though, on its domain. What does that mean? Every point that's on its domain, the limit will just equal f of it, f of the z value at that point. So 0, 0 is not in its domain. That's why that's not working. Okay? Or sorry, 0, 0 is not in its domain, so we can't use this here. But for example, if I change this to the point 1, 0, is that in the domain of this function?
Yes.
Yeah, it'll just be 0 over 1, right? It's fine. It's all good. So the limit just equals the direct substitution of you plugging it in, because it's continuous on its domain. Okay? It's when it's a point not in its domain where it gets tricky. All right, so now the fun part, which is when is a function discontinuous? And I think we were looking at this last week a little bit. And I mentioned when you have holes, but now you can have rips, and then you can have infinite discontinuities. Let me show you what all that looks like. So let me show you a lot of visuals today. The holes one is a little harder to see because it's just a hole, and usually GeoGebra doesn't do that well with that. Whoops. Okay, so here's this function. Notice 0, 0 is not in its domain. But everywhere else, the function will be defined. Like I said, it's hard to see it, but at 0, 0, does it let me actually see? Let me see. Yeah, see, it won't let me do it. But at 0, 0, there's a hole there. So it's like a folded sheet of paper with a little hole that got poked through it. We just can't see it here because it's just a point. It's not showing me. But for example, this one, notice there's a rip. There's a rip, okay, at 0, 0. And I think this is the one we talked about last time, where it's like remember I said you get an X-Acto knife and you just kind of like crease it, the wall at the edge. That's kind of what this is doing. There's like a crease that was ripped up there. And so everywhere else, you have a limit and it equals f of AB, but at that point, you have this continuity through a rip. It's kind of hard to see it. Oh, there we go. Okay? Well, that's new. That's something, you guys didn't deal with this in Calc 1. Here's a different example. Can you guys see the rip in between? There's a rip right there. Right where you can't have y equals 0 on the bottom. And if I bring back these, if I bring this back, y equals 0, that would be the xz plane. So the red axis, here it is. The red axis is x, and then the blue one is, so imagine there's the xz plane slicing through it. That's the X-Acto knife. It's the xz plane. Shot! Nothing on that surface can touch that plane. Okay? Because that's where y will equal 0. All right, and then the infinite discontinuity, in Calc 1, you guys had asymptotes. Your graphs did these things like this, at discontinuities, infinite discontinuities. Here, they do something a little different. Let me zoom out. You don't have an asymptote, you have like asymptotic surfaces. Okay? Notice that this denominator here can't be 0. So you can't have x squared plus y squared equal 1. Okay? Think of this as 1 minus parentheses x squared plus y squared. X squared plus y squared can't be 1. What does that mean? That means that if I look straight down at the xy plane, the circle of radius 1, that cylinder shooting through it is my asymptote. Okay, that circle right there. The surface gravitates towards the cylinder from the inside, but it never touches the cylinder. And then from the outside, it gravitates towards the cylinder, but now it goes down. Okay, kind of like a hole that's sinking. Okay, but it's the same behavior as asymptotes. Okay. So for this continuity, I just want you guys to see what they look like. There will be some on the homework where you have to describe the type of discontinuity. But that's as far as we're going to go into it with continuity, okay? It's just something different that you've never seen. All right, and so if you want to put this for your notes, this function here is the one I used that had a hole. It was x squared y over x squared plus y squared. That one has a hole at 0, 0. The one that had a rip was, I'll just put the last one we saw, which was x over y squared. And has a rip right there. And the one with infinite discontinuity was f of xy is 1 over 1 minus x squared plus y squared. And so for continuity, there's not much else that it's just you guys identifying the type of discontinuity, okay? Given the graph there. And that's it for this section, guys. I showed you a lot, but in terms of what you have to do, it's just the limit parts that you have to do, okay? Showing a limit does not exist, or using polar coordinates to show a limit does exist. It's just that when I teach this class, a lot of students have like all these questions, like, "Whoa, what does this look like?" And so I wanted to show you all that stuff. I remember in one class, I discussed how you can show a limit exists, but I'm not going to have them do it. And we moved on, and they were like, "Whoa, what do you do though to show a limit exists?" And they were very curious. So I decided this time to show you guys. All right. Okay. So the thing we're going to do next is partial derivatives. We're kind of good. Yeah. Okay. Partial derivatives, and it's going to have you guys remember a lot of your differentiation rules, product rule, quotient rule, all that stuff, but with a little bit of a twist. A little bit of a twist. So let's see what that twist is going to be. Partial derivatives. And there's going to be a new notation that you're going to use. All right, and so to motivate partial derivatives, if you've ever gone to the doctor, there's something called the body mass index, which is a scale that kind of shows, I guess, your health and like how healthy are you, a ratio to like your weight and your height. Okay, and so I want to motivate what a partial derivative is going to be through what's called the BMI, body mass index, to kind of give you a sense of what's going to end up happening. So let's consider the BMI, which is the body mass index. I'm trying to show you guys all kinds of applications in this class, so you guys can see how they're relevant.
So something like to show whether you are very obese or.
That's right, yeah. Like, are you too underweight? Are you too overweight?
Yeah.
And they use this scale to kind of measure that in some way. Okay. So of a person, which is defined as a function of two variables, where the M is the person's mass in kilograms, and the H is a person's height in meters. So it's a function of two variables. And the way you calculate the body mass index is you get the mass and you divide it by the height squared. Okay? What I don't know is why it's like that. That's the part I'm not really too sure. Okay? I just know when I researched it up, I wanted to find like how they actually calculate it, and this was the formula that they use. So let's find my BMI. Me, okay? And so I weigh, so maybe you could put Professor Servando. Servando weighs about 190 pounds, which is about, when I try to do the conversion, it was about 86 kilograms. Okay? And has a height of 6 feet 1 inch, which is about 1.85 meters. So if I use my approximate mass and my height here, and I plug it into the BMI formula, I went ahead and I calculated that for you guys, and it was 25.1 kilograms per mass squared. And so then what ends up happening is, in the doctor's room, they have a little scale, and then they look at this number, and then the scale will change depending, and then the scale of those numbers kind of says, okay, you're a little bit too overweight, you're a little bit too underweight. And so then, they'll say, okay, either I need you to eat a little bit more, or, go on a diet, or maybe it's a young child, they're still going to grow. There's still time that, for them to grow. So there's different parameters that can change because there's different variables that are used for this. Okay. So what I want to figure out is, okay, this is my BMI right now. How will my BMI change if maybe I gain a little bit of weight? Okay. Well, those are the questions. Does it change linearly? Right. Will it change? Will my BMI value change? How does it change if I gain a little bit of weight, or maybe if I end up getting a little taller, or if I get a little shorter? And so because of that, that question is a question about rates, and that's where derivatives start to kind of creep in. And so let's see. So it's to analyze the BMI if Professor Servando gains weight, then we need to consider a particular rate, which is going to be, leave some space here, okay? Leave some space here, which is the change in B over the change in what? If I'm gaining weight.
I squared.
Change in what?
I squared.
Well, what are the input variables I'm using?
Listen.
So what if me gaining weight, which variable is changing? Well, that's the thing. And here's the essence of a partial derivative, okay? We're going to assume my height does not change. My height will stay my height. I'm still going to be this tall. The only thing that's going to change is my weight. Okay? So I only want to look at the change in M, but H is fixed. That does not change. Okay? I actually wrote that. This change of rate when H equals 1.85. We're going to leave that as my height. That one does not change. How would you have written this in calculus, this rate, using the notation you guys use in Calc 1? You did dB over dN. Okay, here's where it's going to change. We're only going to use the letter D if I'm using a function of one variable. If I'm using a function of multiple variables, you're going to use a new symbol called the partial symbol that looks like this. It's not epsilon, yeah, it's not delta either. I looked that up. It's called the partial symbol. Yeah. I Wikipedia, I'm like, dude, what is that thing called? I thought it was delta 2. Okay? But yeah, this is the partial symbol. I'm guessing on LaTeX it looks something like that. Okay? So that's the partial symbol. And when you see that, you're telling the reader that B uses more variables than just M. It uses multiple variables. That's how you differentiate. Versus if I wrote this, now I'm telling the reader B only depends on M. Okay? That's the only input variable. So that's the difference there. And then the other thing we can do is we can, to analyze the BMI, if the professor, what did I say here, gets taller, that'd be dope, but no, I don't want to get taller, I'm good. In this case, the rate that you're going to look at is the partial change in B over the partial change in the height. So it's the change in B over the change in my height, but when my weight is going to stay the same, or my mass in this case. What was it, 86? Yeah, 86. So this is where it's going to be a little different. Like you have one input variable changing, but the other one's not going to change. Okay. So we got to figure out how we're going to use derivatives to answer this question. Okay. So we're going to leave it, come back to it once we cover what a partial derivative will look like. Come back to it, use this function to find partial derivatives, and then answer these questions to get these rates. Okay? Let's see. Okay. How much? All right. We'll go on a break in a little bit. A lot of me talking. I apologize. When I have to let this too much. Okay. So to understand how we're going to do this, let's put this application example on the side. And let's go back to our z equals f of x, y, so we can use surfaces and all that stuff that we've been doing, okay? So let's return to functions z equal f of x, y. Okay, leave a lot of room in your notebook. We're going to do a lot of drawings on that. Nice and big. Okay. Let's say this is A right here, and let's say this is B right here. And so then right here is the point AB. And then sketch like some type of surface here. Let's say this surface is above this here. Let's just say I'm gonna make it hella big. Let's say it's something like that. Make it hella big. Okay, that's your surface of your function. Plug in this point into your function, and actually, I was wrong. This should become 0. You get this point, you plug it into f, and then it gives you a z value that will then levitate it so that it has a point. Let's say the point is right here. A, B, f of A. Okay, I'm going to stop there. Imagine you're a little person hiking on the surface. So, whoop, I'm right here. I'm on the surface. Okay, I'm on it right now. Let's say it's my water bottle. This is the point AB. Okay? I'm on the surface of the point AB, F of AB. I'm on the surface. The ground right now is the surface. And the edge of the floor, that's the x-axis. And then this is the y-axis. Cool? Okay, I'm at this point. If I'm going to change the value of x, but I'm going to leave b fixed. Just the way we said I'm going to change one variable, but leave the other one fixed. Okay? I'm walking, I'm here, and I want to walk. I want to walk so that I change x, but I don't change y. In which direction should I walk? If this is the x-axis, and that's the y-axis. Actually, all you guys get up. I'll make you guys go. Everybody get up. Woo! You're getting sleepy, so I gotta wake you up. All right. You're on a point AB. Pretend you're on a point AB. And x is the only thing that changes, not y. Which direction do you walk? Take a step in that direction. Let's say x is increasing. Let's say x is increasing. Which direction do you walk? So that x is increasing and y does not change. You're going to walk this way because that's where x changes, and y, I don't move this way because I'm not changing y, right? All right, go back. I said that. So now I want you to walk in the direction so that y increases, but x does not change. Perfect. Beautiful. Sit down. That was beautiful. Good job. Okay? On the floor right now, right? Z tells me the height that the floor is from the, I don't know, whatever the height. We're in a mountain right now, right? If I walk as x increases, right now on this floor, did Z change? Because the ground's flat. Did it change? No, right? What if when I hike this way, I have to hike up as x changes and I hike up? Does Z change? Yes. What if I hike this way, but now I hike downhill? What happened to Z? Z decreases, right? Let's say I'm in a mountain where when I walk in the x direction, I hike uphill, but when I walk in the y direction, I hike downhill. If I hike this way, Z is increasing, but if I hike this way, Z decreases. Okay? Those rates are how that decreases. That's going to be our derivative. Okay? How are we going to describe that here? Well, as x is increasing, I'm walking in the direction of the x-axis this way, right? So what I want you guys to pretend, this is where the drawing's going to get a little hard, is I'm going to intersect my surface with the plane y equals b. On the plane y equals b, let's say it looks something like this. This part's going to be hard to draw. This is my plane y equals b. On that plane, which coordinate stays fixed? Y has to always be b, right? And it's going to be parallel to the x-axis. So pretend this plane cuts my surface. And it cuts it so that it goes like this. So now it kind of shows me the way the surface is shaped. Okay? I'm standing right here. I want to walk in the direction of x changing. Which way should I hike? This way or that way? I want x to increase. I'm going this way, right? Okay. I'm going to have a tangent line right there at that point. So I have this tangent line like this. Okay? We're going to call this tangent line t of x, because that's the one where x is changing. Okay? The slope of this tangent line is the rate at which z is going to decrease or increase. That's that decrease you guys were telling me. It's like heck. If I'm hiking downhill, that line's gonna go down. But if I'm hiking uphill, that line's gonna go up. If z does not change, that line's gonna be completely horizontal. All right. Now let's do me changing the y coordinate, and x is gonna stay fixed. Now x is gonna stay fixed, so I'm gonna intersect it with the plane x equals a. So imagine there's a plane. There's a plane here. X equals a. Which coordinate stays fixed on that one? X. It's always going to stay a. And when it cuts the surface, let's say it cuts it like this. Okay? So at all these points, x is a. It's only y that's changing, and obviously z. So then at that point on that curve, there's another tangent line called ty. That line is the line where y is changing in that x. And so what we're going to have is that the change of z over the change of x, that rate is going to be equal to the slope of tx, and the change of z over the change of y, that's going to be equal to the slope of ty. Okay? I wanted to draw that so you have that in your notes, because that's going to be very useful when you're doing your homework. Oh crap, I had my screen shared. On the recording, it's going to just show my screen shared, so click on my other screen where I'm lecturing to see me actually lecturing, to see the board on Zoom. Okay, sorry, I had my screen shared right now when I was drawing all that. Okay, let me show you here with an actual example. Okay, here's an actual surface, and I'm a little person, a little ant is right there at that point AB, f of AB. Okay? We're going to let x equal a. We're going to let x equal a. Right now, x is equal to, a is equal to 1. And you guys see that parabolic intersection line right there? Can you guys see it from you guys see that parabola right there? That is the curve of intersection that I was drawing. That's the blue line that I drew here. Right where it intersects it. And this black line is the line of intersection, the tangent line. What I want you guys to notice is that this is the case at this point, at that A and that B. But if I change the value of A, now I'm dealing with something else over here. Depending on the point, see now, if I hike in the direction where y is increasing, now I'm going to hike downhill at that point. Versus if I was at this point, at that point, when I start walking as y increases, I'm hiking uphill. And so the rate would be positive, or over here the rate would be negative. And right smack in the bottom, the rate would be 0. Because right when I move, it's relatively flat there. As I walk, as y is increasing, but now if I do it as x is increasing, now I'm looking at this scenario here. And so notice that if at different points, that stays a positive slope, versus if I'm on this side, it changes. So I just kind of wanted to show you different scenarios because I can't draw all that and move it. Okay? But that's kind of where we're headed. Let's take a break and we'll keep going. Whew. All right, good. Let's take a break.
So the problem is like
hold on. Come back at 2:05. Zoom at 2:05. Okay, say it again.
So problem set 5 is it covers this one.
Problem set 5 is gonna cover what we're doing on Thursday. What we're doing on Thursday. It covers this and what we're doing on Thursday.
Okay.
Yeah.
So the first question is it will be on Thursday. The first question.
Correct. It's gonna be what we're doing today. Yes. Yep.
And the second is on Thursday.
Second, yeah. So today we're gonna do this. Partial derivatives. And Thursday we're gonna talk about something called linear approximation. Okay. Is that your guys' homework? All right. Thank you. Thank you. Oh, dude.
I can.
Can you go to the division office? Do you have a stapler?
Yeah. Also for the tangent line for 3D graph, what would it look like if A and B were both zero? With a point in the A direction or the direction?
It would look like, you mean like if they were both at 0 right here?
It would just default to pointing the X right now.
Yeah.
Pointing the X?
What do you mean, point on the X?
Well,
You're saying if both A and B are 0, right?
yeah. Because if you, because the tangent line will rotate to the y-axis depending on what the slope is. Like if you, for example, change, which is the y direction to A?
The y direction, if you change, you mean like if you want to change what y?
If you change B, won't it rotate?
If you change B,
Yeah, so change B. No, it's okay, no, it just goes in the X. Okay.
it'll depend on the surface too. Yes. Yeah.
So you know how like there's the one with the theta and the r.
Yeah.
So now when you do like let x equals to r cosine theta
Yep.
and then y equals to r sine theta. And you said like it only works on like a origin. Like can't we just like for a point A or Z, can't we just like plus A and plus B?
Technically, you could do that too.
Oh, yeah, okay.
You can.
And that just works, right?
It works if the function's nice.
Oh, right.
Like if your function, like if you had to take the limit of something gross, like either the absolute value of x, y, or something.
Yeah.
Like in that case, it might get a little bit more challenging. Well, that's what I was trying to say earlier. You look at the function. Sometimes you can get creative with the algebra. Yes, that's an option. You can always try to get creative with the algebra using all this stuff.
Okay.
But for some functions, it's just like no matter what algebra you do, like like if I have something like I don't know, maybe not inside of the log. Why? Like just like really gross things.
Yeah.
Like it's hard. Like you can kind of get away with it, but then at some point maybe you can't cancel the r's completely.
Oh.
And like then you're kind of stuck.
Yeah.
And so that's what I was saying. Like in that case, like there's no other way. Then you have to prove it.
Right.
And you have to prove it. Okay. Yeah. But yeah, totally. You could totally try that method. Yeah. Because what you're doing there is you're looking at circles centered around this point, and then now you're going like this instead of doing it at the origin. Yeah, that's kind of what's happening. All right, let's see. I think Garrett was here. Yoshinobu.
Homework in general is horrible.
T, right?
I had to go back to sleep, I would have left. I was gonna take 6 hours. Have like a yeah. Wait, I actually will. Vote on an hour. We will like 9 hours. 8 hours. 7 hours. 6 hours. That would be 60. Really good sound. Five. And then 5 to 4 is that that's not 5 to 6. So anything less than that is just.
It's actually interesting. And then it seems to be that very confused. Start writing it after an hour. Just be
I'll be right back.
So here's I can graph this because I get to like 1 a.m. and I've been like 1 a.m. So and then I run my I think it's 2 techniques. All of a sudden, why? And then it's like I'm unstoppable. Like I don't look at the clock for like 2 seconds. And then all of a sudden, it's moving. Yeah.
And that's what I did. I like I have a distraction like on. I'm not that adrenaline rush.
Yeah. No, that's true. That's true. Let's see. This is
Never did it like
I didn't see my exercise in the stack, Professor.
Say it again?
I didn't see my exercise in the stack.
These are ones I need to pass back.
I thought that would be
30
just.
seconds before time.
No, these are old ones that I remember I passed out a bunch of them. They weren't here that week, so.
That's cool. That's really
I'll share my screen. Whoops.
Page down.
Oh, crap.
Like their names and dates.
Okay, whatever. All right, guys, we're gonna keep going. We're gonna keep going. Okay. Remember, this might be a little bit, it's okay to feel a little uncomfortable with it. It's new. We'll look at some examples, and I'm gonna try to show you guys a bunch of different examples to kind of, you do the algebra, but then again, tie it back to the visual, okay? Because as you notice, this class is very visual. Okay. So, like I said, if we want to we want to fix y and vary x, I want you guys to picture this scenario here. We're changing x here, so you got this orange curve. So how are we going to actually define the derivative here? So here is what we're going to call the partial derivative of f with respect to x, long title, at AB. And so we're going to write it like this. The partial derivative of f with respect to x is, do you guys remember in Calc 1 you guys learned prime? You would say f prime. But here, there's two different primes. There's going to be one with x and there's going to be one with y. So we don't use prime notation. We write f and then you write a little subscript x like that. That means the partial derivative of f with respect to x here at the point AB means that you're going to take the limit as h goes to 0. Your difference quotient here. Which variable are we changing only? Only x. So it's going to be x plus h, and then, it's going to be a plus h, and then b, that one stays, minus f of ab over h. So notice the only thing that's changing here is the x coordinate. And like I said, this is the slope of your line tx. This line right here. And then similarly, the partial derivative of f, with the long title, with respect to y at that point, similar, partial of f with respect to y though. So this time you're going to write f, but with a little y in the bottom. Partial f of y, that's how you read that. Partial f of y at AB is going to be the limit as h goes to 0, but this time it's the y that's changing. So a stays a, now it's b plus h minus f of a over h. So the thing to realize is this part right here. And this guy represents the slope of that line ty. Okay. Question, yeah.
In the second one, you had f of a comma h, but in the
Oh.
first one, you have f of a comma b.
Sorry, there you go. My H looked like a B there, apologize. So again, kind of like with Calc 1, you learned that derivatives using the limit definition, okay? And then you realize there was differentiation rules that you used, but because they were proven by the limit definition, okay? So what we're gonna do is we're gonna find these derivatives, and we're gonna apply the differentiation rules that you guys learned in Calc 1 to see how you're gonna compute these partial derivatives. So there's kind of a big leap here, okay? So what we use differentiation rules. Differentiation rules from Calc 1 to find partial derivatives. And then let's look at some examples. So here's where it gets algebraic. And I'm really gonna do this one step by step and break it apart so you guys can see it, okay? So find the partial derivatives of f of xy equals 1 plus x squared plus y squared. All right, so this is what we're going to do. If I want to find the partial of x, I'm going to assume y is fixed. Let me show you how we're going to do that. So to find partial derivative with respect to x, assume y is some fixed value b.
So that means y is a constant.
It's a constant. It's a constant b. So think of, I'm trying to find this partial here. Pretend like I had you guys do on the problem set, where I told you guys, remember there was a table with the wind chill index, and I had you guys describe what the functions represented. One of them was, you said this is the index when the humidity changed, but the temperature stayed fixed. And then the other one was the index when the temperature changed, but the humidity stayed fixed. I was preparing you for this part, okay? So pretend this is now a function where only x is changing, but y is going to stay fixed, okay? So to find this partial, I'm going to take the partial derivative with respect to x, kind of like when you guys wrote this in Calc 1, but now with partials, of this function, but I'm going to pretend the y variable is some constant b like this. Okay, you're going to pretend it's some constant b. If you were to do that, now you go back to Calc 1. You say, what's the derivative of a constant? 0. What's the derivative of x with respect to x? 2x. What's the derivative of this other constant? 0. So then your answer would be 2x. That's the thinking that you're going to want to do in your brain. So when you're doing partial of x, if you want in the beginning, you can replace the y by some value b, some constant, if you want to start. Okay? No.
In general, we could just treat y like a constant though.
Exactly. So this is what your head's going to do. This is what the textbook's going to do. They're going to say, so to find the partial derivative of this function here, they're going to leave y as y. You take the partial derivative of 1 plus x squared plus y squared. But when they do this step, because you're doing partial with respect to x, your brain needs to train itself to see y as a constant. So when you take this derivative, you say, what's the derivative of a constant? 0. What's the derivative of x with respect to x? 2x. What's the derivative of this other constant? 0, and so you get 2x. Okay? This is how the textbook shows it, but this is what you want to do in your head if it helps to see y as a constant. Okay? So then this would be the answer for the partial with respect to x. Let's do the other one. So to find partial of y, what do you think we're going to do?
Let X.
Constant. I'm using a just so it matches with this. So that means that now when I find this partial, I pretend a is a constant and I only have a function of y. So that when I take the partial derivative with respect to y, in my head, I picture 1 plus a squared plus y squared. And so now I got to look at my variable that I'm differentiating with respect to. The derivative of a constant, 0. The derivative of this is a constant as well, 0. And then the derivative of y with respect to y is 2y. So then my derivative is 2y. That's what you do in your head as you're starting this out. But then the way the textbook's going to do it, they leave everything in terms of x and y, and then to take this partial derivative of this function, you need to train your eyeballs to see that this is partial with respect to y, so all x's are constants. So the derivative of a constant is 0, the derivative of another constant is 0, and then the derivative of this is 2y. Okay. Okay, let's see. Questions on that? We're gonna do a harder example. Okay, I'm gonna get that chicken wing and I'm gonna make it really spicy in a little bit. Okay, back to my hot ones analogy. Okay, I wanted to start with this easier example here. Okay, cool. Kind of. Okay. Now, do you guys remember how when you found the derivative, it was a function, and then you use that function to give you the slope of the tangent line? Okay. So what we found is we found the partial derivative with respect to x is a function. It's a function. It's a function of x and y. It just happens to only have an x. Okay. It's a function of x and y. It just happens to have an x. The partial derivative with an x and y, the partial derivative with respect to y, is also a multivariable function. It's just that the expression only happens to have a y. Okay. So these partials are supposed to give me these rates, these slopes of tangent lines. Okay. I'm running out of room here, so I'm gonna have to erase your beautiful drawing. Damn it, I did it. No, let me go over here. So let's consider let's consider a point. Let's plug in an actual point now. Okay? That point we're gonna plug in is like the point AB. Okay? So consider here, I'm gonna erase this part because I really want that picture there. Consider the following at the point -1, 1. Let's plug that point into the function itself. Into the function. What do we get when we plug it into the function? What is it? We get 3, right? Okay. What does that 3 represent in terms of this picture?
Z.
It's the z coordinate. It's that z value right there. That's what z represents. This is the z coordinate of the point -1, 1 on the surface of F. just the way in Calc 1, when you plugged in x into the function, it gave you the y value, right? Here, this gives you the z value. But now, let's plug in that point into the partial with respect to x, which is this function. What do we get when we plug in that point? There's no y, right? So we really just plug in the x coordinate. What do we get? You get -2. And when you plug it into the partial with respect to y, which was this function, you just get 2. Okay. See this point that's on the surface? Some surface? I'm on the surface. I'm at that point. I'm at the point -1, 1, 3. If I walk in the x direction and I increase a little bit, am I going to walk uphill or downhill? It's going to be a negative rate, so z is decreasing. But if I walk in the y direction as y increases, I'm going to be walking uphill. So that's the information this is giving you. This is the instantaneous rate at which z decreases at the point -1, 1, 3 as x increases. And so yes, it's going down because it's negative. This is the instantaneous rate at which z increases, because it's positive, increases at that point as y increases. Cool. You can see that? Now, if I plug in a different point with some other coordinates, it'll give me a different point on the surface, kind of like what I was trying to show you in GeoGebra. And then you plug them into the partials, and then it'll tell you how you're increasing or decreasing. Okay, let's do one more example, and then I'm going to have you guys do a bunch of them. So you can actually, I've been lecturing way too much today. And here, let me, you guys have it in your notes. All right, let's see. I'm going to take it up a notch now. Let's find the partials, that's shorthand for partial derivatives, of f of xy equals 3 sine of xy squared plus x ln of x squared. A lot nastier than the polynomial we just did. Please ask questions on this one because this one's nastier. You guys ready? Yeah, Charlie. The textbook's going to be formal, say partial derivative. And you're showing you some math fun. Like making you part of the cool club. Okay, here we go. So let's see. I'll go slow. I'm gonna have you guys help me out here. We're gonna take the partial with respect to x. Sam. It will. You can do algebra before, just the way you did in calc. Yep, you could do algebra if you want. I'm not gonna do that, so I can end up using the chain rule. Okay, just to see how it plays with all these partial steps. Okay. When we're doing this, what is a constant? Y is a constant. Okay, when you see this here, Y is a constant. So in Calc 1, how did you take the derivative of this? What did this equal? This equals 3, right? So now, what would that be? What's my constant here? X is the variable. This is a big fat constant, right? So what's the derivative of x times a constant? Just a constant. So it'll just be y squared. See that? So the derivative of x times a constant is just a constant. The derivative of x times a constant is just a constant. Okay, let's see. So I'm going to take the derivative of this bad boy with respect to x. Okay, see this y squared? Pretend is just a 3, like I showed you there. So we got to do chain rule. Take the derivative of the outside. What's the derivative of the outside? Cosine. We leave the inside alone. And then we multiply it by the derivative. I'm doing step by step here. The derivative of the inside. Like that. That's chain rule. Okay? What rule do I have to use here if I don't do what Sam was saying and move the 2 out here? I just leave it like that. Product with a little chain, right? So I have to use the product rule. The derivative of the first function is 1 times my second function times plus, sorry, I leave my first function and then I take the derivative of the second function. Okay, let's see here. So here's that step that I was showing you. This is the part that starts to get a little hard. So this is, what is this right here? What's the derivative is just a constant, right? Y squared plus, this is just ln of x squared. What's the derivative of this bad boy? 2x over x squared, right? And then the x's will cancel. So then we end up with 3y squared cosine of xy squared. Is that cool? Does that look good? Yeah. Plus ln of x squared. And then here, what happens with this x and this x? Cancels out, so we just end up with a 2. Okay, cool. What's the partial derivative with respect to x? Do you guys see how it is, in fact, a function of both x and y? Okay, it is a function of both x and y. This is with this example, it was a simpler looking function. Okay. Questions? Anything you want me to repeat? I know I'm going slow, but okay. All right, let's do partial of y now. All right, I still have to do chain rule because I have a y inside here. So it's still going to be the derivative of the outside with the inside alone. But now it's a partial derivative of the inside with respect to y. Plus, here's where it's weird. I'm taking the partial derivative with respect to y of this whole thing here. I'm taking the partial of y. What is a constant? It's x, right? X is a constant here. So if x is a constant, Are there any y's here? It's all x's. It's all a bunch of constants. So what is the derivative of this here with respect to y? Perfect. It's gonna be 0 because it's just a big fat constant. Yeah, this is a big fat constant. So then I'm gonna end up with what is the partial derivative of this with respect to y? It would be like me doing something like this. Or this calc 1. Let's take it to calc 1. It's like when you guys did this. There was a constant times y squared. So what did the 2 do when you did it? Multiplied with this constant here, right? And then it was just y. So here you just bring the 2 down and then multiplies with the constant x. So it's going to be 2xy. Right? Cool? Reading your eyes. Oh, I really know what's going on. Okay. All right, looks pretty good. Okay, so then this gets multiplied with the 3. So it's 6xy cosine of xy squared plus salud, plus big fat 0 because that's a big fat constant. So then your answer is just 6xy cosine of xy squared. Very different from this function, right? So let me see. I'll leave this here. All right, you guys want to try some now? All right, let's do it. All right, a lot of enthusiasm. Let's go. So let's see. I have 3 that I want you guys to try. Find the partial. Here, I'll be 4. So do it for this nice polynomial function, x cubed plus x squared y cubed minus 2xy. And then we got, make it a little nastier now. We got e to the xy squared, that's an exponent, plus x sine of xy. And then the third one, I want you guys to answer the problem from the beginning of the section. B of mh is m over h squared. You guys got the tools now to do it. So with your classmates, just make sure you guys check each other, see if you're in the right path. Go slow. Careful with those mistakes. You two here to check. Okay, I have you to check. And then I'll have to check with each other. Let me include, yeah. And I'll have you guys. Do this, and if you do, Right. Try it out. Be careful with those differentiation rules. Oops. I found a mistake in my notes. Let me fix that. We'll go around and have your questions. Come in.
That's correct.
So, well, right now, so what you have is you have this electronic discussion. So it's a little bit of advanced
Yeah.
product form.
Okay. This would be the two.
Correct. So you take the derivatives just like.
Okay.
All right, guys, if you haven't yet, can I just have you guys share each other's answers? Take a look at each other's work real quick. Check real quick. Real quick little check-in, guys. Quick check-in.
I'm stuck up here. I can't Oh yeah, I got the two there.
How's it going?
Yeah.
Questions? Yeah. I'm gonna put the answers on the white. I could do the second one. Let me just write the answers and then I'll do the second one because I'm probably gonna ask.
You're right, it's y squared, not x y squared.
All right, it looks like most of you guys are having a hard time with number 2, so let's do number 2 real quick. All right, let's see. For number 2, what rule do you have to do for the first one? You gotta do chain rule first. Then you have to do chain rule because this is e, and then there's this function inside of the e to the x. Okay? So you have to do chain rule. So it's going to be the derivative of the outside function, which is p again, okay, with the same function inside of it, times the partial derivative of the inside function with respect to x. So a little bit of chain rule. Okay? Is that cool? Chain rule? Okay? Let me see I'll write all these calculus rules over here to remind you. Remember from Calc 1, the derivative of e to the function was e to the function times the derivative of the function. That's kind of what's happening here. If this is bugging you here, then you're going to want to review chain rule. Okay? Then I want to do some review of the chain rule there. Of course, come and I'll help you out. All right, now for this bad boy, this has an x and this function has an x. And they're multiplying. So what rule is that? Product rule. How did you guys do the product rule here? How are you guys doing it? F prime g like that? There's different ways to write it. Okay, let me go off on that. I'll use that. So this is like my f, this is like my g. So my derivative of x with respect to x is 1, and then just my other function, plus the derivative of g with respect to x. When you take the derivative of g with respect to x, what do you have to use? Chain rule. So it'll be the derivative of the outside, which is cosine, with the inside function, times the partial derivative of the inside with respect to x. This is all g prime. That's all g prime times just f, which is just x. That's that rule. All that is g prime. This whole piece right here. Okay, so let's see. So then we get the derivative of this is with respect to x. What is that? It's just a constant y squared. So I'm going to get y squared e to the xy squared. And then for this guy, we just get sine of xy. What's the derivative of this with respect to x? It's just y. Oh, someone's wrong. Is that Siri? Careful there. So x times y, and then cosine of x times y. And that should be the answer.
Yeah, no, that's not minus cosine. Oh, never mind, I'm thinking bigger.
Is that the integral? Yeah, it's the derivative. So yeah, this question in itself just has like almost all of the calculus topics on the differentiation. Jacob, yeah.
I don't know if this is legit or not, just kidding. Is there like a partial antiderivative?
Correct. once we get to derivatives or integrals. Yep. What a concept will come into play. We're gonna differentiate or integrate, but with one variable being constant. Okay. So that's your partial with respect to x, guys. Did this help with this breakdown here? I think this is the one that was bugging you guys, and for some of you this one. Okay, now when it comes to partial with respect to y, let's see. So again, there's a y variable in here, so we're gonna have to use chain rule again because there's some function of y in there. If there wasn't, like let's say this was cosine of x, what would be the derivative of this with respect to y? Are there any y's? Just a big fat constant. So then it'd just be 0. But because there is a y, it's not a constant. Okay? So I gotta do chain rule. So the derivative of the outside function is e to the function. So e to the same thing. And it's a partial derivative with respect to y of the inside. Now that I'm taking partial derivative with respect to y, is this the product of two y functions? No, it's just a constant here, right? So it's only this, it's just going to be the derivative of sine of a constant times y. What's the derivative? Let's do, here, let me write it like this. Pretend it looks something like this. Pretend it looks something like that. X is a constant, right? So I just have to do chain rule. The derivative of the outside function, which is cosine, right? But with my constant multiplying it. Okay, the derivative of this part is cosine times the constant x with the function inside of it times the partial of the inside function. So it'd be like me taking the derivative of that. This is 5 cosine 5 of y times the derivative of 5 of y. All right, help me out here. What is that going to be? 2x, that's right. You bring down the 2, that's y. And what is this going to be? It's just a constant x. So then you're going to get 2xy e to the xy squared plus x times x cosine of xy. So just be careful with these, okay? Really go step by step. Be careful with the dance of product rule with chain rule. Similar things that were hard in Calc 1 will come back here. All right, what did you guys get for the partial of b with respect to m? 1 over h squared. This is just a constant. And the derivative of b with respect to h, negative 2m over what? H cubed. Now, going back to that problem from the beginning of class, if I wanted to find how my body mass index changes as I gain a little bit of weight at the point that I'm at right now, did anybody figure that out? It would be around, you plug in these values into this function, and you would get something about 0.26. Okay? Versus if I plug it into this function, and I see how is my body mass index changing according to where I'm at, but I get a little bit taller, it's going to be negative 27.2. Okay? So which parameter affects the BMI the most? Height or my mass? Hell of my height. I change my height just a tiny bit, my BMI really decreases by a large value. But if I gain a little bit of weight, it only increases by a little. Okay? You guys look tired. You look tired. But I got more fun stuff because I got higher derivatives and then I got higher dimensions. It's gonna be dope. It's gonna be dope. Math is sick. It's just sometimes, it's a little tiring. All right, let me show you what the heck I meant by just the way you guys did, second derivatives and third derivatives. These are again functions of x and y. So they have their own partial derivatives. Okay? So we're going to call this part higher derivatives. Not too crazy though, not too crazy. How many partial derivatives do you think this guy will have? Well, how many variables are the input variables? So it has its own partial derivative. How many? Partial with respect to x and partial with respect to y. What about this one? 2. So how many total second derivatives will there be? Good times, 4. Okay. So since partial derivatives are also functions of x and y, they also have partial derivatives. Partial derivatives. We're almost done. But I really want to make sure you know as a notation. Okay, so let's say I take the partial with respect to x. And I want to take the partial of it with respect to x again. What do you think we do? It's just xx. Okay? What is this doing? It's taking the partial derivative with respect to x of the partial of f with respect to x. That's what it's doing. So if I think of it as fractions, how many partials do I have on the top? 2 of them. So this is how we're going to write it down. We're going to write partial squared of f is the partial of x and the partial of x on the bottom. You can write the partial of x squared if you want on the bottom. Question?
Yeah, I was just wondering, about the multiplication with
It does cover that, but we're not covering infinitesimals in the class. But it does have to do with that. Yeah. Okay, and then we have, if I take the partial of y and I do it with y, it's going to be f of y, partial f of y, which is the partial of y of the partial of f with respect to y. Ooh, we're going to write it like this: partial squared of f, partial squared y, partial squared of y. All right, that one's not too crazy, not too different. But here's where it gets a little weirder. Let's say I decide to take the partial of x first, and then I do the partial of y second. What does this mean? I'm taking, what did I do first? I did the partial of f with respect to x first, and then I took the partial of that with respect to y. So on the top, we end up with, I'm taking the partial derivative twice of f. But now the order, according to the way it's written here, you're gonna write it like this in the textbook. So what I want you guys to be careful with, so you don't get this wrong, is the order. When you use the prime notation, which is the subscript notation, you go from right to right. But when you use the instantaneous rate notation like this, you go from right to left. So be careful, okay? This goes in this direction, this one goes in that direction. And then similarly, if I do y first and then x, I take the partial of x second, and I take the partial of y first. This is going to be partial squared f, and then I'm going to go from right to left. I did y first, and then I did x second. It goes this direction, this one goes in this direction. And then you can keep going, but I'm not. Okay? You could take 3 partial derivatives and so on. Okay? So this is what we're going to call higher derivatives. And then there's the different scenario. Well, what if my function is not a function of just 2 variables? What if it's a function of 3 variables or 4 variables or 5 variables? Okay? So we're going to call this higher dimensions. And be careful here with the notation. So if f is a function of n variables, I'm going to go extreme and just say in general n. How many input variables does it have? N. N. So this is how we're going to write it. F of x1, x2, ... xn. Okay. Equals, if there's n variables here, what should we call this one? If this is 1, 2, blah, 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 3, or sorry, n, this one is going to be called n plus 1. The next one. So if I want to take the partial derivative of f with respect to the ith input variable, like let's say the second one, what's going to be constant when I do that? Everything else will be constant. So if I take the partial derivative with x, xi is the only one that's changing. Everything else is going to stay the same. It's going to stay a fixed value. Okay? So then this is going to be denoted this way. But the key takeaway here is you consider all other input variables except xi to be constants. Okay? That's the key takeaway here. So if I put all your grades in my grade book, okay, and I want to study the rate of the class average and how it changes, and I only want to see how Dylan affects the class average, then I'm going to look at the partial derivative with respect to his grade changing only, and all your grades stay fixed. You see that? Okay, that's what this is doing. All right, sweet, we're at 15 minutes. So here, I'll just give you guys one last practice problem, and then we're done. All right, so for f of x y, z, w, where this is just a big fat monomial, x squared, y cubed. Ay, hijo de su madre. Sorry, that scared the crap out of me. My Spanish came out on that one. That's on video too, that's awesome. I meant holy moly. Okay? Z to the fourth and w to the fifth. Okay. This is what I would like you guys to find. Your partial with respect to y, partial with respect to w, partial with respect to yz, and then partial with respect to wxy. Okay? You guys can do it. I believe in you. Yo, this hella scared me. Yeah, but
Is there any convention to the order you write the variables in when you take the partial derivative? If you keep them in the same order, you have them there, or like if we're treating everything except y as a constant, should we have y at the end and after the other ones?
if you want to rewrite it like that to help you out, you can.
Does it matter in the final answer? Just in terms of like convention, I guess.
What, say it again.
Just like if you write the y between x and z or at the very
Oh, you mean like alphabetical kind of thing?
yeah.
Normally you try to be alphabetical, you're right. I should have, normally the z would have been on this side, yes, by convention, but it's okay if you don't. Yeah, it's okay if you don't. Yeah. Correct. Correct. Well, this one is the second portion. So think of it like this. So to do this one, right? What you're really gonna have to do is you have to take, you took the partial derivative of f. Which one did you do first? Why? Because you go from left to right. And then whatever you get for this answer, which is this, you take the partial derivative of that with respect to z. Okay? Yeah, so here, I'll write it in this notation here. See if that helps you out.
And it just like automatically put it back in the order. It's like, just like, your concepts and look at it.
X squared, y squared. It's actually not number 4.
Yeah, kind of fun.
No, I feel the same way because you know, I think we're like I don't know, like it's more so, especially after
This is right.
I was doing that one last night, and I got to the point where my brain just shut off. So like,
There's two problems like that. I worked the first one out, and then just like A prime.
as soon as I get to like really nasty that I don't want to write it down, you're doing the cross multiplication, you got it over two. No problem.
All right, guys, you can check your work on the board.
I do not want to write I probably will, the equation, but not until I have to.
Let's see, I made a mistake, right? Yeah, it should be 5. With respect to, it should be 5. There we go. For number 2, let's see, maybe I made a bunch of mistakes. So you're going to take the derivative of this with respect to z, right? Yeah. It's 3, there you go. Hella mistakes. I'm just putting that to see if you guys are like, you know, on top of it. Yeah. Compare and contrast. All right, here, let's see, that one, yeah, that one should look good. Okay. Let's see. Okay, so we'll stop here, guys. What we're gonna do next week, or on Thursday, is we're gonna, remember how you guys found derivatives to find equations of tangent lines? We're gonna use partial derivatives to find equations of tangent planes. Okay? And then I'm gonna cover the chain rule with multiple variables. Cool? All right, but we'll stop there. Good job, guys. Today was rough, a lot of lecture. I apologize. But good job, guys. I collected your homework. If you haven't turned it in, please turn it in.